Hello, welcome to Ready to Derive. In this video, we explore limits involving infinity. In particular, we look at two cases. The first is when a function tends towards positive or negative infinity as x approaches a finite value from the left and/or right. This signifies the presence of a vertical asymptote. The second is when a function approaches a finite limit as x approaches plus or minus infinity, signifying the presence of a horizontal asymptote. As always, there will be plenty of practice problems to keep it real. Hope you find it helpful.
So let's start, as always, with an example. So consider this function 1 over x minus 1 squared, and from the table, let's see if we can figure out the limit of this as x goes to 1. Okay, so if we approach 1 from the left, we notice that y is getting actually pretty big. 1e8 means 1 times 10 to the 8, so pretty big number. And if we approach from the other direction, from above 1, then y is also getting pretty big. But notice it's not actually approaching a finite number. It's just getting larger and larger and larger. And as far as we understand, limits are usually about approaching a specific number. So in the last lesson, we would have just said this doesn't exist. But as we're going to find out, we're going to get a little more nuanced about this. So let's look at the graph of that function. As we see from the graph, which was also verified in the table, is as x approaches 1 from the left, the values of y are heading up to infinity, and from the right, again, imagine hopping on the curve. From the right, as x approaches 1, you're heading to infinity. So now, our more nuanced take on this situation is, instead of saying the limit doesn't exist, in the finite sense it doesn't, but instead of that, we are actually going to say that the limit of this function is infinity because that is where the y values are tending towards, and they're tending in the same direction. So a couple of caveats. Remember, we're just describing behavior, so this is useful in describing the behavior of the graph at a particular value. The limit still does not exist technically, so if you were a DNE, you wouldn't be wrong for the answer for this. And that's because infinity is not a number. So we sort of use it as a number, but it's not really a number. Interesting stuff. So we can sum this up with kind of a definition of what makes an infinite limit. So the limit of a function as x goes to a, we say it's infinity if we can make the values of f arbitrarily large, that means as large as we like, by taking x to be sufficiently close to but not equal to a. And notice that it also, the limit of a function could be negative infinity also, so we could have something like this, where we have a vertical asymptote, and we have a graph tending like this. So if this is a, the graph at a is, there's a vertical asymptote, and then y is tending to negative infinity. Actually, the cat is out of the bag now. So what I want you to see is that when we do have an infinite limit, that's a sure indicator that we have a vertical asymptote present. So let's look at another example, the function y equals 1 over x minus 1. To compare, we were just looking at 1 over x minus 1 squared. What happens to the graph if we remove the square? So we have what is called a hyperbola, and I've indicated with the red dotted line that there is a vertical asymptote there. And here's the table to help us in our analysis. So we are going to look at one-sided limits now. That's how we evaluate whether a limit exists, by looking at the one-sided limits. And so as x approaches 1 from the left, so approaching 1 from the left, we hop on to the curve, and we are heading down to negative infinity. And you can see that again in the table, as x gets infinitesimally close to 1, right? As close to 1 as you like, y gets infinitely large in the negative direction. And what about as x approaches 1 from the right? Hop on the curve where your y-coordinates heading looks like positive infinity. Let's check the table. As x approaches 1 from the right or from just above, gets infinitesimally close. Y is getting infinitely large in the positive direction. But because these limits don't match, we say that the overall limit as x approaches 1 does not exist. The graph is heading in different directions. So here's a few more examples with some common curves. Here we have a log or an ln graph, the ln of x minus 1. And right now you are asked, what is the limit of this as x approaches 1 from the right? This is 1. So approaching 1 from the right, the graph is heading off to negative infinity. Here's a graph of tan x. And from this graph, as x approaches pi over 2 from the right. So here's pi over 2, approach it from the right, hop on the curve, also heading to negative infinity. Notice while we're here, if we want to describe, say, the behavior here, we would say that the limit as x approaches pi over 2 from the left of tan of x equals positive infinity. And here we have a graph of cosecant squared x. And notice I haven't put a one-sided limit here because if you notice from the left of 0 and the right of 0, the graph is heading to positive infinity. So we can say that the limit as x goes to 0 is infinity. And the one-sided limits also would be infinity. So not to be outdone, what about horizontal asymptotes? So let's go back to the graph, the function we were looking at originally. And while we were focusing on where is the function heading to infinity, we also have some stuff going on in the horizontal direction. So we now will begin to ask, what happens as x goes to infinity on this graph? So let's, instead of approaching a particular value, let's allow x to head to infinity. Where are the y values heading? And if you hop on the curve and head towards positive infinity, your y values are getting closer and closer to 0. And actually, as x approaches negative infinity, which should be going in this direction, you're also approaching 0, indicative of a horizontal asymptote along the x-axis. This brings us to a definition of what it is to be considered a limit at infinity. So we say that the limit of a function as x tends to infinity exists and is equal to L if we can make the values of f of x as close to L as we like by taking x sufficiently large. Notice once again, we could also have the limit as x goes to negative infinity of f of x equals L. I don't want to leave out negative infinity. So limits at infinity as opposed to infinite limits. Infinite limits go with vertical asymptotes. Limits at infinity are indicative of horizontal asymptotes. Let's look at a sort of more interesting example. This is a function that looks like it has two asymptotes going on, actually. So the limit as x tends to infinity. So as x tends to infinity, it appears that y is approaching a value, and that value can be shown algebraically. We're not doing that right now, but that value is 4. So the limit as x approaches infinity is 4. Notice that the curve so-called crosses the asymptote, and people often get a little confused because they think things shouldn't cross the asymptote, but an asymptote, a horizontal asymptote is about what happens as x approaches infinity. So it's not really talking about what's going on close to 0 or anywhere else. It's what's happening at the tail ends of the curve. Similarly, so as x goes to negative infinity, so we're heading x value in that direction, hop on the curve, it appears we're also approaching, but in this case, -4. So the limit as x approaches negative infinity is -4. 2 horizontal asymptotes on this curve. So let's look at it. What should be a familiar function, y equals e to the x. And let's describe the end behavior using limits. So as x goes to infinity, x is moving in this direction, we hop on the curve, we look like we are heading up to infinity. Not a very interesting, perhaps, observation, but one you should really think about. This, you should commit this to memory, that e raised to a very large number, so e raised to, say, the 10,000 is going to be huge. So even if I didn't give you a graph, you should be able to determine the end behavior even without a graph by just thinking conceptually through what the magnitude of the number might be. In the same way, if we think about as x goes to negative infinity, so x heading to negative infinity, it appears that y is heading to 0. How could you think about this? Well, you could think of e to a very big negative number. E to the negative 10,000 is 1 over e to the 10,000. 1 over a huge number is going to be very small, tending towards 0. So once again, e to the x is very good to be able to determine these limits with exponential functions without having a graph and just being able to think through logically. So we're going to end with some practice where we're going to transition away from relying on graphs and just try to reason through these limits conceptually. So let's take the first one. As x approaches 3 from the left of this function. So what I'd like you to do, sorry about this random mark here, is see if you can plug in. Can I plug in 3? Well, you can plug in 3 to the top. 3 plus 1 is 4. But I can't plug 3 into the denominator. That would give 0. So I'm going to plug something just to the left of 3, say 2.9999. And I realize that if I subtract that from 3, I'm going to get a number close to 0, especially as I get closer to 3. But it's going to have a negative kind of charge to it. And now I want you to see that 4 divided by 0, in the negative sense, 4 divided by a very tiny number is going to get huge in the negative direction, negative infinity. Let's move to the next one. Same reasoning. 4 on the top, but now I am coming at 3 from the right, so a number slightly bigger than 3, but very close, approaching 0, but from the positive direction, and then think 4 divided by positive 0, in a sense, is positive infinity. Now, because these limits don't match, then when the limit as x approaches 3, not from the left or the right, but overall, doesn't exist. Can't describe the end behavior there. Let's go to, now what happens if we add a square around the denominator, in this one here, this example here. Same reasoning. Put 3 into the top, we get 4. Can't plug 3 into the bottom, but if you approach from the left or the right, you're getting closer and closer to 0. But because we're squaring in a positive sense, 4 divided by a tiny number is going to be huge. And because that tiny number is going to be positive, it's going to be, the limit will be positive infinity. Now here's a change of pace. Now we're going to consider as x goes to infinity. Well, you can't sort of, if I plug infinity into the numerator and the denominator, I'm sort of going to get infinity of infinity. And are there magnitudes of infinity? Perhaps. So we're going to tease this apart a little more. If I plug in x equals 10,000, if you look at the numerator, 2 times 10,000 cubed is going to be huge. The plus 1 is going to be negligible to that. Similarly to the bottom, you can just forget about the minus 2 in thinking about what's happening as x gets to infinity. Even the minus 3x is going to hardly make a dent. The overarching value is 2x cubed over 5x cubed is what's going to kind of dominate the function when x goes to infinity. And because these match the x cubes, you can kind of fudge this a little and think about, well, they don't even really they're going to match in a sense. And so what the overall limit is going to be is 2 over 5. And you can see that if the denominator, say the denominator had a power of 4, so if the denominator had a bigger degree, then the limit of this function would be tending towards 0 because that 4 would be overwhelming the 3 in the numerator. This is kind of pre-calculus stuff, so you could go back and review your material on rational functions. All right, let's go to this one here. As we approach 2 from the right, so this is the way to think about it. It's e to the 1 over 2 from the right is going to be 2 minus 2.001. So it's going to be 0 in the negative sense. And 1 over 0 in the negative sense is going to be negative infinity. And we know from the slide before that e to the negative infinity is heading to 0. So this limit's equal to 0. What about the limit as x approaches negative infinity of cosine x? Well, here you have to kind of know about the graph of cosine. Cosine just oscillates between -1 and 1. So here the limit does not exist. And what about this last one? Here you have to think about magnitudes. So as x approaches infinity, 2 to the 10,000th power is going to be huge. Bigger, in fact, than 10,000 squared. So you have to realize that the denominator is going to overwhelm the numerator, and the limit of this function will be 0 as x approaches infinity.
And that brings us to the end of this lesson. I hope you found it helpful, and if you did, please do click like and/or subscribe to my YouTube channel, Ready to Derive. Thank you.